Have you ever noticed how differently water and honey pour? One flows freely, while the other is slow and sluggish. This property, this internal stickiness of a fluid, is what we call viscosity. Today, we're going to explore what it is and how to measure it. Imagine dropping two marbles into two different fluids. In water, the marble sinks almost instantly, but in honey, it moves much more slowly. This resistance to motion is a direct consequence of viscosity. Honey is much more viscous than water. We can think of viscosity as a kind of internal friction. In a high viscosity fluid, the internal layers resist sliding past one another, which is what slows the marble down. Let's build a simpler model to understand this sliding action. Forget the complexities of a falling sphere for a moment. Let's consider the simplest possible case, a fluid sandwiched between two flat plates. The bottom plate is fixed in place, but the top one is free to move. To get the top plate moving, we have to apply a force. This force isn't just to accelerate the plate, it's a constant push needed to overcome the fluid's internal friction, its viscosity. The stickiness of the fluid is constantly trying to slow the plate down. It's helpful to imagine the fluid as being made of countless thin layers. The very top layer of fluid sticks to the moving plate and travels at the same speed. The very bottom layer sticks to the stationary plate and doesn't move at all. The layers in between are dragged along, but each one moves a little slower than the one above it. This creates a gradient of velocity, a smooth change in speed from the top to the bottom. This relationship is the heart of viscosity. The shear stress, which is the force we're applying per unit area, is directly proportional to the velocity gradient. And the constant of proportionality, the Greek letter mu, is the viscosity. Now, how does this relate to our problem? Our problem involves two cylinders, not two flat plates. But if the gap between the cylinders is very small, we can imagine it's just our flat plate model wrapped into a circle. The top moving plate becomes the inner rotating cylinder, and the bottom stationary plate becomes the outer fixed cylinder. The physics is the same, but instead of a linear pushing force, we now have a twisting force, which we call torque. In this setup, we rotate the inner cylinder at a constant speed and measure the torque required to do so. Just like the force on the flat plate, this torque is working against the viscous drag of the fluid. Through a bit of calculus, which relates our linear model to this rotational one, we arrive at this formula. It connects the torque we measure to the viscosity we want to find. Since viscosity is what we're trying to find, let's rearrange this equation to solve for mu. Now, we can solve our problem. We are given all the information we need: the torque, the dimensions of the cylinders, and the rotational speed. First, we calculate the gap width L by subtracting the inner radius from the outer radius. And we need our rotational speed, N, to be in revolutions per second, not per minute. With all our values in the correct units, we can now substitute them into our equation. Let's calculate the top and bottom parts separately. The numerator is straightforward. The denominator involves a few more steps, but it's just arithmetic. Dividing these two numbers gives us our final answer. The viscosity of the liquid is approximately 0.242 Newton-seconds per square meter. So, we've gone from a simple observation about marbles in honey to a precise physical measurement. This very principle is used in real-world viscometers, all by measuring the effects of that fundamental property, fluid stickiness.